Thank you very much. So I thought I'd start my talk just telling you a little bit about myself. It's not a lot to tell, but I was actually, I'm Korean. I was born in Seoul in 1969. And when I was a year old, the family moved to Canada for a new life, like a lot of immigrants. And while in Canada, the Korean community was quite tight. And I had the pleasure of learning what little Korean that I know at home from my parents, from my grandparents. And so the Korean that I use is 경상도 사투리, because both of my parents are from Daegu. 그것도 참 열심히 배웠습니다. And but then in 2008, I was very surprised to get the Hoem Prize. And that's one of the honorable awards here in Korea. I think I'm still the youngest person to receive that prize at the age of 38. But they told me that I had to give the acceptance speech in Korean, just 2 minutes. And so no matter how hard I tried to learn all the words in Korean, the vocabulary is quite high. And so I gave my acceptance speech, and nobody in the audience understood anything I said. And so to this day, of all the Hoem Prize winners, I was speaking Korean, but in the videotape, we have Korean subtitles on the bottom, because nobody could understand what I was saying. So that's the legacy I'm leaving behind. I'm here to tell you a little bit about the emergence of personalized medicine, and specifically, there's so much that we can talk about on personalized medicine, but I want to give you a few of my thoughts, perspectives from the Jackson Laboratory and my time there. As many of you know, medicines conventionally is based on population averages, and in many cases, drugs don't actually work for the patients. This is some of the data that has been touted around, where 25% of the drugs used for cancer are effective, 30% for Alzheimer's, 50% for diabetes. And so clearly the need for understanding how to personalize medicine better, and particularly with understanding more about our genetics, is really important. It's the next great challenge. And I think we've made, over the past few years, a lot of progress in this area. In fact, there are more than 200 genomic-based medicines on the market today, and certainly more to come. And the idea here is that even now, but even further on, more and more powerful genomic tools and understandings will make personalized medicine the normal treatment for diseases. So there's a lot of areas that we could do, but we have limited resources, so we got to focus in on certain areas. And so eventually I came up with these 5 components: cancer, microbiome, immunology, human genetics, and I purposely put computer sciences in the middle, overlapping these 4 areas, because it was my opinion, and I think it's correct, that all of these areas will heavily rely on state-of-the-art computational scientific capabilities. So let's see some of the areas that we've developed platforms to build this up at Jackson Laboratory. So certainly in the area of cancer, the world has made a lot of progress in personalized medicine in cancer. Ever since the identification of the Philadelphia chromosome for CML by Janet Rowley at the University of Chicago, we now know a lot of consistent breakpoints and fusions that occur for specific cancer types, and those then become targets for new therapeutics. But at the same time, I also realized that immunologists were learning more about genetics, and that immunology was very complex, but it seemed to be tied in so many of the diseases that we're studying. And so having an ability to build on these 2 areas, build some critical mass, seemed to be important. And so one of the platforms that we built at the Jackson Laboratory was a very immunodeficient mouse. So it's a mouse that has basically no immune system, developed by Lenny Schultz at the Jackson Laboratory, originally to study diabetes, but certainly could be used for cancer studies. And how is that possible? So, for example, there's something called the patient-derived xenografts. These immunodeficient mice allow us to grow human tissues, including human cancers, in the mice, just like they would grow in the human body. And by doing so, we could then do DNA sequence or RNA sequence analysis. We can freeze those materials. We can propagate it more so that the more and more mice have the same tumor growing in them. And so this was something that we started also in Korea, initially at Seoul National University, and then transitioned to Ewha Women's University. This is a slide showing gastric cancer. As you know, in Korea, gastric cancer is one of the most prevalent cancers in the country. And by chopping up that cancer, you can actually take one of these immunodeficient mice, using a trocar, put that tumor under the skin of that mouse. And if you notice carefully here, you'll see a little bump under the skin, and that's the human tumor being grown up in that mouse. And so back in 2017, we'd already successfully established more than 300 of these PDX models that came from Korean patients. So these were cancers of Asian origin, specifically from the Korean population, everything from breast cancer, gastric cancer, lung cancer, colon cancer, and so forth. And so once you've built this PDX resource, what can you do? You can then treat them with different drugs and drug combinations, and just to see which drug or drug combination makes that tumor regress or grow smaller. And so by using that, in Korea, we were able to publish several studies now showing how we could combine different drugs and get more insights into the tumors that were being developed in Korean patients. And this is just one of those examples. But of course, with immunology, we know that cancer immunotherapy is a very hot topic this day. Cancer cells produce antigens that are exposed to the cell surface. And T cells, their normal job is to identify these foreign antigens. And then long-term exposure of these antigens can upregulate PD-1 expression on T cells. However, the cancer cells sometimes can trick the T cells and produce receptors that'll bind to those PD-1 receptors and tell the T cells that I'm one of your own cells, don't attack me. And so basically, immunotherapy makes those blocks and doesn't allow those the PD-1 and PD-L1 receptors to bind, allowing the immune system to do what it's supposed to do, and that is to kill the cancer cells. And so by using these mouse models now, we can actually take those mouse models that have no immune system, put in your favorite human immune system, put in your favorite PDX tumor, and then your antibody of choice, and see whether it's non-effective or effective in its treatment. And certainly, the bet on cancer immunotherapy was good, and in fact, in 2018, it was heralded as worthy of the Nobel Prize. James Allison, Tatsuku Honjo jointly received it, and so I think this really sets the stage for a lot more work moving forward. The third area that we thought would be very impactful in personalized medicine is the microbiome. This is a relatively new area of study. We're now recognizing that if you take all the cells in us and on us, actually there's more bacterial and viral cells that reside with us synergistically as human cells. And the microbiome really does have a lot of potential impact for understanding human diseases. This is just some of the areas where the human microbiome can have an impact in our understanding of human diseases. But just to give you a feeling as well, it can be used in diagnostics. For example, every year, 1 million babies worldwide die within the first 10 days due to infections, and this is just a baby in the neonatal ICU. At the Jackson Laboratory, some of our microbiome researchers have developed a test where they can actually sample the stool samples from the babies in the neonatal ICU and sequence all the bacteria in there and find from day to day which bacterial colonies are increasing or which are decreasing, and can predict not only what bacterial infection that baby is going to come down with, but also get an insight into what resistance to which antibiotics it has, because you have the DNA sequence of the bacteria. So this is just an example of one of the powerful ways that the microbiome is impacting our understanding of human diseases. And since we're talking about commercialization, I think this is one of the areas that is really booming in terms of companies, startup companies that are setting up. This is just a list of companies on the East Coast of the United States that has come up in the last couple of years centered around the microbiome. And so finally, human genetics. And human genetics and computer science I'll put together here, and I'll tell you why. So this next slide tells me reminds me of a lecture that I heard where, as being human like all of us, and especially after lunch like this, I remember listening to a lecture, and I heard the word digital, and then I think I fell asleep a little bit, and then woke up and I heard the word mouse. And so in my mind, I had digital and I had mouse, and I forget what was in between. But it made me actually think, digital mouse, what is a digital mouse? And if there is something about a digital mouse, the Jackson Laboratory, with all its 90 years in mouse genetics, should be involved in it. And so we actually firmly believe that the next step in advancing human genetics is actually to develop precise and predictive digital models of human diseases. And this could be mice, this could be flies, this could be C. elegans, but certainly because we have experience in the mice, that's where we'd like to be concentrating on. So what do I mean by this? Well, in order to get true personalized medicine, you would imagine that you have all the mutations, if you have all the information on genetic diversity, the environment, how your organs respond to every insult, and then over time, you would get all the information that you need to get predictive precision medicine. But unfortunately, that information is not all available for humans. We know a little bit about diversity, we get a little bit about the environment. We can't biopsy your brain at intervals throughout your life, and we're getting a little bit of aging. So there's deficits here that need to be filled in. And so if we had a perfect or a working digital model for human diseases, like the mouse, and using that, we could hopefully fill in the necessary information to get us closer to precision medicine. So what does that involve? Well, this is what Jackson Laboratory is hoping to call the CUBE Initiative. So the CUBE Initiative is like this. You have all the genotype information, you have all the phenotype information, and you have information, let's say, across environment, it could be across time, and so you have this data block for a given disease or for a given organ, etc. And clearly you're not going to have all that information, you'll have spots of it, but that's okay. When we actually look at all of that data for human, this is probably what we have, because we can't get all that information for humans. You'll get some of the information on the cube, and lots of it will be empty. If we then look at a model organism like the mouse or the Drosophila, etc., we can genetically manipulate that organism. We can put it into specific environments, do a lot more control of it than we can for humans. So you can actually build a similar information cube for that model organism, and then from extrapolation, getting vectorization of the data, you might be able to then cross over some of that information to fill in the space for the human. And so this is our idea of how to revolutionize human genetics by using these precise model organisms. And so, again, the idea here is to get precise human, precise medicine in humans. You can't do it by big data alone, just from human information. And as we actually sequence more and more individuals, the one thing that everybody that in this field agrees upon is that we find more and more variants of unknown significance. We need to understand and to functionalize those variants. And you can functionalize them in cells, but if you want to understand what that function is in the entire organism, you have to use a model organism. And so this idea of being able to take the model organism and the data from it, incorporate it into the human, and build that cube for information. So the Jackson Laboratory also understands the difficulties in implementing precision medicine in the US and elsewhere. And so I do want to point out the fact that we have now every year been holding a healthcare forum. The dates for this year's forum is October 23rd, 24th, where we connect the decision makers across the healthcare industries and promote dialogue between the innovators, entrepreneurs, insurers, providers, investors, and policymakers to find new areas to bring about precision medicine. So in the last few slides, I just wanted to share with you one scientist's thoughts on how we can enable personalized medicine. So first and foremost, and I know this from experience, precision medicine research is expensive. And so in order to do precision medicine research, we need more funds. And I don't think there's a simple answer to how to get those funds. But what we found is certainly we want to be thinking as a society on diversifying the funds for research. Private funding for the sampling of 25 US nonprofit research institutes over the past few years have actually shown that they are increasing in the last 2 years by 40%. More private funding is going into research in the US. And in fact, it's a great time to be in life sciences because about 87% of the funding in 2017 actually went into life sciences. And so certainly the private funding, the philanthropic funding is incredibly important to tap into. In Korea, of course, we've had companies such as Samsung, POSCO, etc., that have for a long time been investing in research. More recently, I've had the pleasure of doing some grant reviews for the Silicon Valley Foundation that is also now starting to support early stage innovative research to the tune of $250,000 to $425,000 US per year for 5 years. I can tell you that the research programs that I've been able to review for this program have been absolutely outstanding. These have really been phenomenal quality of science. And then, of course, patents is something that we need to be paying attention to. Now, as a director of the Jackson Lab for Genomic Medicine, I'm constantly thinking about how we can encourage the faculty to be thinking about patenting or containing the IP rights for their discoveries. Here you can see some of the research institutes that are well known and the number of patents that they've received compared to the number of faculty. That can be impressive, but one of the things I'll show you here is on the left-hand side, the Broad Institute at 206 patents across 200 faculty doesn't seem to be very good. But of course, it's not just the number of patents, but what are the impact of those patents. So as you know, one of the most critical patents that have been made recently that has affected personalized medicine is the patents around gene editing technology, which the Broad Institute has successfully won the patent rights for that, as well as a follow-through on it. So it's actually estimated that the patents for gene editing CRISPR-Cas9 technology will easily be in the billions of dollars in its worth. So that's something that we need to certainly pay close attention to. I think in genetics, there's a lot of new technologies that are driving science very quickly. We as a society need to have global responsibility and have a global voice for resisting non-ethical legal abuse, ethical legal abuse of genetic technologies. And of course, most of you will know Dr. He in China, who recently used gene editing technologies to create the first germline human gene-edited babies in China to try to make them more resistant to HIV infection. This was condemned worldwide, including in China, for its actions, and a reminder to us of responsible use of these technologies. I think we also need to reduce barriers. Over time, it's interesting that we as a community have placed a lot of artificial barriers to the use and the interpretation of genetic information in medicine. At the Hugo meeting that was just held in Ewha Women's University last month, one of our plenary speakers, Leslie Biesecker from the NIH, actually tackled this problem quite elegantly and showed comparatively how people in genetics and in medicine actually are too overly cautious about their interpretation and the use of that information for medical intervention. And I don't know why we've done this. Maybe it's just the technologies are moving so fast it's hard to catch up with. But this is doing a disservice, I think, to enabling personalized medicine. And at the same time, we want to recognize the limitations of certain genetic availabilities, specifically the direct-to-consumer genetic testing from companies like 23andMe, Ancestry.com. These are exciting because they tell us a little bit about who we are and give us some information that helps our curiosity. But in some ways, like if you are looking for a medical test, a medically relevant test, you don't just go and get that test. You go and see your physician, you get proper counseling, etc. And I think those lines are starting to become blurred with the widespread use of direct-to-consumer testing. Next, I think we need to provide more education to the clinical providers. That includes the medical doctors, the nurses, genetic counselors. And in the US, in fact, we are most of the people in the US are agreeing that we have a major shortage of nurses and genetic counselors that can facilitate all of this genetic information that have healthcare implications. And so any of you that are in medical education will know that the amount of genetic education you get as a medical doctor is quite small. And for those of us that are actually practicing genetics, it's hard to keep up with it as it is. So this is something of major importance, I believe, to enable personalized medicine. And finally, to be able to increase the amount and the quality of the genomic-focused clinical decision support tools will be critical. What do I mean by that? So in some ways, if you look at a radiologist will interpret complex data from an X-ray or from an MRI, and with the help of computational algorithms, he or she will provide a diagnosis that will be sent to the primary care physician. And so the radiologist is a consultant to these physicians on what is cause of a disease and what are their findings. And in some ways, the radiologist of the genome is like the medical geneticist, taking all of this data, the information that we're garnering from DNA sequencing testing, RNA sequencing testing, targeted testing, etc., and to be able to interpret that complex data through complex algorithms to the doctor. But the problem is not a lot of energy and resources are going towards making those computational infrastructures readily available for those clinicians. And again, I think that's hindering the implementation of precision medicine. So in closing, I am absolutely convinced we are living in an era right now where at some point, each and every one of us will have our DNA sequenced, whether at the prenatal stage, whether at genetic screening after birth, whether through direct-to-consumer testing, whether through the time when we get cancer and we have our cancer cells sequenced. At some point, I think we all are going to be having our DNA, possibly RNA sequenced, and with all that information, I think it's really important for us to be able to enable personalized medicine in a way that's most beneficial to the patients, but also cautionary about its abuse. So with that, I'd like to thank you for your attention and my talk. Thank you very much.
Thank you. It's a really, really great pleasure for me to be here because I feel very passionately about communicating science and our achievements to a general audience. And so my talk today will not be very much about the science that we do, but more about how we can communicate our science. So I will have 3 parts in my talk. In the first 5 minutes or so, I'll try to explain to you what quantum nanoscience is and why you might be interested in that field. Then I will comment a little bit on my take on basic science, what makes basic science important, and how can we achieve good basic science here in Korea. And then I will talk about general outreach. So let's get started. Our motto is engineering the quantum future. By this we mean using quantum mechanics, the theory of quantum mechanics that describes essentially everything, to create a better future. So QNS is laying the foundation for future quantum technologies, but we are part of the Institute for Basic Science, so our mission is to perform basic science to lay this foundation. We are located at Ewha Women's University here in Seoul, about half an hour taxi ride away. And before I get any further, let me, with the deepest heart, say a big thank you to you all. You are making it possible for me to do this research here in Korea through the IBS system and through Ewha Women's University. So thank you very much. Now, one slide, why is this research field maybe important today? We already, in our current technology, and our companies here like Samsung and Hynix are leaders in semiconductor technologies, we are running into problems by the fact that we're making our devices so small that we arrive at the atomic scale, and these quantum mechanical effects are really important in our current IT technology. But a more interesting take on the same subject might be that we want to use quantum mechanics to do entirely new things, such as quantum computation and quantum sensing. And this is really what drives a lot of passion nowadays in this field. But as I said, we at the Center for Quantum Nanoscience are allowed to perform the basic research that underlies these things. Now, this is a worldwide research effort going on right now. There is incredibly large amounts of money being spent in the United States, in Europe, also in China and many other parts of the world. So we are in a community that is really being developed as we speak. A little bit more specific, what do we actually do? We are working on the quantum behavior of individual atoms that we can put on a surface and we can control with spectacular precision. So we are not so much interested in making devices, but in understanding the properties of atoms and molecules on surfaces. My specific research tool is the scanning tunneling microscope. I will not explain to you how this works today. That's a different talk. But we're also interested in other uses of, for example, here we have a defect in a diamond material which we can control with optical means. This is the field of what we call quantum nanoscience. So this is all I wanted to say about my own personal research. So let's focus a little bit on the bigger question. How can we do great basic science research? And the most important thing, and I cannot stress this enough, is to give basic scientists time. We need time to do great basic science. You cannot get basic science done from tomorrow because we need time to get great ideas, to ask the right questions as we learned today, and so it takes time. There's many, many examples. I want to just mention two here. There's an example from Leonardo da Vinci, who, as we heard earlier, was an artist, a poet, an engineer, and also a great scientist. And he was supported for his whole lifetime for his work in Italy. A more recent example, and this is really important, I think, for the basic science funding, is the recent work on the detection of gravitational waves in the United States. This is work that was predicted, the theoretical predictions came from Albert Einstein in his theory of general relativity about 100 years ago, but it took a long time to be able to make experimental machines that could measure at that precision. And this precision is truly mind-boggling. But here, looking at the timescales, it took from about 1980 to 2015, so that's 35 years of continuous, large-scale financial support to be able to make these machines that can make these breakthrough discoveries. So 35 years is a long time scale, in particular here in Korea, where everything has to change fast. But if you want to do something as great as detecting gravitational waves, you need time. So how do we create such an environment here in Korea? We need stable funding. We need autonomy to decide ourselves what research we want to do. And, as I said before, we need sufficient time to achieve the scientific breakthroughs that we're all looking for. Now, I came to Korea specifically because of the Institute for Basic Science and the opportunity to create a research center with stable funding, autonomy, and sufficient time to be able to succeed. So I believe that this Institute for Basic Science is exactly what we're looking for in this context. But let me say this here, Kicho kwahak kiu lon myon, bali bali buto bolyola. Get rid of bali bali. There is no bali bali in basic science research. Right? A year is not a lot of time for us. Sometimes we can't get anything done in a year because things just don't work. We need time. And so this is a very important concept that I can't stress enough here, especially in the context of Korea. Okay, this is my recipe for basic science. And now for the rest of my talk, I would like to focus on how we can communicate our basic science to a non-scientific audience. And why do we do this? Because we want to create enthusiasm in all of you for the work that we do. Because you are, in the end, the ones that are supporting our research efforts. So how do we communicate science to a general audience? Let me start with how we normally communicate our science. We write papers. Like here's a paper that we published at the end of last year, and the title is Hyperfine Interaction of Individual Atoms on a Surface. I would say as far as scientific papers goes, this title is reasonably understandable, right? You have individual atoms, you have a surface, maybe you know what a surface is, maybe not, but you certainly don't know what the hyperfine interaction is, right? And so if I go to this journal was published in Science, if we look in this Science journal, there are many articles that I can't understand at all, even though I am a scientist in basic science. So we've chosen to communicate in a way that we even can communicate with experts that are just a little bit away from our own research field. So this is targeted only for experts in a very small subfield. Now, if we're lucky and we have great research results, then sometimes the general media, like newspapers, like our sponsor here, or the TV can help us to promote our research. So let me play this little clip here.
기초과학연구원 양자나노과학연구단이 홀뮴이라는 물질의 원자에 정보를 저장하는 기술을 개발했습니다. 산화 마그네슘 기판 위에 홀뮴 원자를 올려놓고 미세 탐침으로 전기 신호를 주면 원자의 자성이 위아래로 바뀝니다. 이 변화를 철 원자로 측정할 수 있는데 이를 통해 0 또는 1이라는 디지털 신호를 읽어내는 겁니다.
So here we made these animations. We hire animations firms to try to bring this research a little bit closer to you. But I could probably ask you right now, and you would still tell me you don't understand what we're doing. Right? This is still too complicated. Even the KBS news channel cannot make this digestible to a general audience. So we need to do more if we want to communicate with a general audience. And so this brings me to 3 examples that I've selected from our work that we're doing here. The first one is a YouTube channel that we've created as part of our center, and this really is supposed to reach out to all of you. The second example goes back to my work at IBM before I came here to Korea, and is about the world's smallest movie. And this is important because it shows you how difficult and how expensive it is to do really great outreach. And the third one is an art contest that we have going on this year. So let's look at our YouTube channel. If you look at the contents that we have here, some of it is describing our research, but most of it is really geared towards non-scientific audiences, like the science talk that we have here, the Meet Q&S, and also the Engage the Community. So we are actively working on creating contents that is something that you should really enjoy. And I want to play you 2 clips here. The first one being from the science talk given by one of our German postdocs, Philipp Wilke, who is really an expert communicator, as you will see, and he will describe the basics of the scanning tunneling microscope for you.
The object in the middle is the microscope they actually got the Nobel Prize for, the scanning tunneling microscope, which allowed scientists to create images of atoms. Here you see one of the first images they took using that microscope, showing the surface of a silicon crystal, an important material for electronic devices. Each white dot marks the position of an atom here.
And you can see he's very animated and he really loves explaining basic science concepts to a non-scientific audience. So this is contents I think we need to create more of. I always say that if I do research that I cannot explain to my grandmother, then I'm doing something wrong. I need to understand my research at a level that I can explain this to anybody. The second one I want to show you is a clip from one of our students. As we said in the beginning, I work at Ewha Women's University, and of course, as the name says, that means that all of our students are women. And I want to show you this clip here from one of our students, Safa, who's from Bangladesh.
I mean, I've always been interested with sciences, but physics is something, it's like a father of all other subjects. For me, physics has been one of the most interesting subjects always, and I think it's the curiosity. After starting physics as an undergraduate subject, the more I studied, the more I loved it, and I just want to keep on studying it. Never happened with me with any other subject.
I love her enthusiasm, right? She can't stop studying physics because the professors apparently have done such a great job of teaching her the passion that you need for physics. And as we learned earlier today, passion is really what we need in order to create great research results. Now, I don't know if Safa is going to be a really great scientist. She's still young and in the process of being developed into a scientist, but she has the passion and the enthusiasm to make that work. And I think with YouTube, we can show that researchers are normal people, that we are all humans, and we are in this adventure together because we are passionate about science. So now, let me focus on a slightly different aspect. I used to work for IBM, a very large international company, and I was in the division of nanoscience research. And the company at the time was supposed to or wanted to be seen as a leader in nanotechnology. And so it made sense for the company to say, let's take the money that we normally put into a marketing campaign, that is about $1 million to make a TV marketing campaign, and rather than giving this $1 million to the TV companies, let's use this to promote our own researchers and create contents. So the scale of this project that I'm describing to you right now is $1 million US. Now with this, we created the world's smallest movie. The idea was for IBM to put itself in a younger audience light. IBM is traditionally a business-oriented company that wanted to appeal more to our audience here, to younger people, and they wanted to do 1 million views on YouTube. Before, they didn't have any videos that had 1 million views. My own personal goal was to encourage young people to study science and technology. This is still very passionate to me. Now, how can you do this? we hired a marketing firm, Ogilvy and Mather, one of the very big marketing firms in Manhattan in the United States, in New York. And they, of course, said, we need to tell an emotional story. If you want to reach people, you cannot tell a purely scientific story. You have to tell an emotional story, because emotion is how we communicate with each other. But we want to tell an emotional story with science. And so the creative company came up with the idea of the boy and his atom. So on the right, well, I don't know which side, one side here, you see the atom coming close to the boy, and the atom starts dancing with the boy, then the boy starts dancing, and then both of them dance together. And the most important part here is the end. It says, the boy and the atom dance together in harmony, they are friends. So in very few strokes, these geniuses create an emotional connection that actually works. Now, the difficulty, of course, is that we want to tell this story with atoms. And so let me give you one slide here on why this is difficult. Of course, atoms are really small. We put these atoms on the canvas that we paint on, which is a piece of copper here. You see it here on the side. And this piece of copper is about as big as a coin, so 1 centimeter or so in dimension. Now, how small is an atom in comparison? So if a single atom was as big as this coin, then how big do you think that coin would be if I scaled everything up by that factor? The coin would be as big as the entire planet that we live on, right? So we are scaling down from the size of the planet down to a single coin, and that is, of course, why the work on the atomic scale is difficult. But, of course, we have these tools at IBM and now also at Iowa Women's University. We have these tools that allow us to work with single atoms. And so then the creative company hired a layout design, and so they figured out how many dots does it take to make this boy, because we can't make it with strokes, because every atom is a dot, and so we needed to make it as dots. And so then we converted this into a real frame. So this is now an image on the atomic scale taken with the scanning and tunneling microscope, where you see the boy made of 90 atoms and the single atom on the side. And of course, now we have to animate this and make them dance together. So let's do that. So it looks so simple here, right? But every single one of these atoms we have to position with atomic scale control using the scanning tunneling microscope. It took us, a team of 4 people, 10 days, working 18 hours per day, essentially non-stop, to make the frames for this movie. My own personal involvement with this project was on the order of 3 months. So 3 months of my time went into making this project work. And again, we spent about $1 million on this campaign. So why? Because IBM wanted to use this as a marketing campaign. They wanted to achieve 1 million views, and we got 1 million views in a single day. The first 2 days, we got 1 million views each. And this is, of course, only possible because of outreach over all the social media and traditional media channels that were available because of that large budget. My personal goal was to encourage young people to study science. And this is, of course, a little bit harder to measure, but let me give you a couple pointers as why I think this actually succeeded. The first one, there were really excellent comments on YouTube. They were asking questions like, why don't we see the atoms underneath the atoms that we use? Or what are the waves on the surface? All of these questions are really interesting scientific questions. Also, this movie was published in 2013. We have now something like 8 million views on this. And it's still active in 2019. We just received a gold medal on a Reddit sub-channel. So people are still very interested in this. And most importantly to me, over 1 million people watched the 5-minute movie that describes in detail how we do this, why we do this, and why it is important to do the basic research that underlies this movie. So I think this was a great success, but you have to recognize that this level of success is very, very difficult and also expensive to achieve. Now, finally, I want to end with the art contest. This is something that we actively have going on right now, and maybe you have some friends, or maybe you are artists yourself. The idea here is we want to share our research to a community that is non-scientific, and we specifically chose artists as a target here. Engage with them to introduce our research center and have them learn about quantum science and nanoscience, and possibly also decorate our new research building that EWA is building for us. We're moving in next month, so maybe we can use some of the art to decorate our building. This is geared towards general audiences and students, and the rewards are kind of interesting. The monetary reward maybe not so interesting, something like $3,000, but the awards will be given at the award ceremony during a large international conference which we're organizing in September, and the winners will participate in a banquet with the president of EWA Women's University. So this is, I think, is a really special honor for the participants. So how do we engage the artist community? We have one student, Jin Kyung, who was an undergraduate in physics with a minor in art history. So she was the perfect person to take on this task to communicate art and science together. She made a beautiful article, 2-page article, on the relationship between art and science. She explained quantum duality, superposition, entanglement, really complicated quantum mechanical concepts in a really fun and engaging way. She also gave a talk at EWA. We didn't know how many people would come, but it turned out, this is Jin Kyung here in the front, 70 artists came, overfilled the room. We had to sit on the floor. I wasn't even there. I wasn't involved in this at all. She gave a 30-minute talk, and then she had 100 minutes of questions and answers. Together with the postdoc you see in the back, Wonjun, who really is very passionate about explaining the science aspects of it, the two of them really handled this apparently really beautifully. This led to a Naver post where we got over 6,000 views, and we didn't have to pay for this. I heard that 6,000 views on Naver, that channel would cost you something like $10,000 typically. And most importantly, 500 people downloaded the contents, and they are studying about quantum nanoscience now in order to convert this into art. So let me give you 2 examples here of what Jin Kyung explained to this audience. The first one is on quantum duality. Is light a particle or a wave? In the 1800s, there was a big debate in the physics community whether light is a wave or whether light is a particle. And of course, we now know light is both a wave and a particle, depending on how you look at it or which experiment you perform. At the same time, the Impressionist movement, of course, dealt very much with the concept of color in art. And one particular person here, Georges Seurat, used the particle nature of light by not drawing with strokes, but to make individual dots and create the beautiful artwork where each color is created by individual dots of fundamental colors. So this is an interplay between art and science. Now, the second concept I want to show you is a little clip that Jin Kyung again created. In the quantum world, we have the superposition. So
두
let's
번째
listen to
양자의
her.
성질은 불확정성의 원리입니다. 양자역학 세계 이전에 기존의 세계에서는 만약에 사과가 사과나무에서 떨어지는 것을 본다면 우리가 이 사과의 질량과 순간순간의 위치와 속도를 알고 있으면 이 사과가 어느 지점에 어떤 힘을 가지고 떨어질지를 쉽게 예측할 수 있습니다. 하지만 양자의 세계에서는 입자들은 확률적으로만 존재하기 때문에 우리가 이 입자의 운동 상태를 정확하게 안다는 것은 불가능한데요. 이러한 것을 슈레딩거의 고양이 이미지로 잘 아실 수 있습니다. 아주 작은 세계에서, 양자의 세계에서 아주 작은 상자 안에 아주 작은 고양이가 있다면 우리는 이 고양이의 상태가 죽어있는지 살아있는지를 정확하게 알 수가 없습니다. 그래서 이 고양이는 50%는 죽어있고 50%는 살아있다는 그러한 상태로 묘사가 되는데요. 그리고 우리가 만약에 억지로 이 상자를 열어서 이 고양이의 운동 상태를, 어떤 고양이의 상태를 확인하려고 한다면 우리에게 절대 정확한 정보를 알려주지 않습니다. 왜냐하면 그것은 확률로만 존재하기 때문입니다. 그래서 이러한 불확정성의 원리를 자신의 작품에 적용시킨 작가들이 있는데요.
So I just want to point out that she's of course speaking. She is now a second-year master level student. She's speaking to an audience in this case YouTube, but also in giving the talk, she doesn't really know. She must have been nervous for a long period of time. She told me that she hasn't even watched this video because she's so nervous about seeing herself on the camera, right? But I think she can do an amazing job at trying to bring these complicated concepts to a general audience. And I'm really looking forward to see what the results of this art contest will be. Okay, finally, how do we do long-term basic science? This is just repeating what I said before. We create an environment with stable funding, autonomy, and sufficient time to achieve breakthrough results. This is really what we need to do if we want to create great basic science research. Now, why do we do this? Maybe more importantly, why do we do this? We heard here that it's all about the economic development, right? I really hope that this is true, but for me, it's a little bit smaller. Why do we want to create basic science research? We want to create world-class basic science. At my center, it means engineering quantum systems on the atomic scale and studying their quantum behavior. We want to train the next generation of Korean leaders in science and engineering. And of course, the specialty that we have being at a women's university is that all of our students are females. And so hopefully, we can contribute to creating a large number of female scientific leaders for the future. And finally, we want to develop the foundation for future technologies, and in our case, that is the technologies that underlie the field of quantum sensing, quantum computation, and quantum communication. So this is really why we do the basic science research, in particular for my center. So with this, I'd like to thank you for your kind attention.